The classification of protoneutron star (PNS) oscillation modes is crucial for understanding the physics inside these objects and the associated gravitational wave (GW) emission. This study applies three different classification methods to PNS non-radial oscillation modes: Cowling classification, Generalized Cowling Nomenclature (GCN), and classification based on Modal Properties (CBMP). Utilizing PNS models from 3D simulations of core collapse supernovae, the research investigates the evolution of oscillation modes. In the early stages of PNS evolution, typically before 0.4 seconds after the bounce, the Cowling classification is inconsistent. However, the GCN and CBMP provide complementary information that helps to understand the evolution of the modes. The GCN reveals several avoided crossings as the mode frequencies evolve at early times, while the CBMP tracks the modes across these avoided crossings. Notably, the strongest emission of GWs by the PNS corresponds to the F mode in the GCN, indicating that the mode trapping region alternates between the core and the envelope at each avoided crossing. At later times, approximately 0.4 seconds after the bounce, the three classification methods present a similar description of the mode spectrum. The study also tests universal relations for PNS modes according to their classification and finds that the behavior of the universal relations for F and P modes is remarkably simple in the CBMP. These results have implications for understanding the physics of compact objects and the associated GW emission. The PNS models used in this study are based on 3D simulations of core collapse supernovae, which include the effects of microphysics such as electron capture and neutrino emission. The simulations also capture the changes in the equation of state, EOS, inside the star as it cools and becomes more compact. The EOS at high densities is still largely unknown, making the study of PNS oscillations and GW emission crucial for understanding the physics of compact objects. Detecting gravitational waves from core collapse supernovae is challenging due to the complexity of the processes involved. However, numerical simulations have led to a general understanding of the signal morphology. A future detection of gravitational waves from galactic core collapse supernovae will provide valuable insights into the physics inside the protoneutron star and facilitate tests of simulated models. Accurate knowledge of the waveform morphology is crucial for developing effective algorithms to extract gravitational wave data from detected signals. Various methods have been proposed, including principal component analysis, Bayesian analysis, denoising techniques, and machine learning. The excess power coherent wave burst search is a promising approach for detecting gravitational waves from nearby core collapse supernovae. This work adopts a theoretical framework developed to study stellar perturbations, describing the gravitational wave signal of a supernova as the superposition of the oscillation modes of the protoneutron star. Oscillation modes can be classified based on their main restoring force, with P modes driven by pressure and G modes driven by buoyancy. The standard classification, based on the Lamb frequency and the Brunt-Väisälä frequency, is insufficient for stars with complex dynamics, such as evolved stars and newly born protoneutron stars. Alternative classification methods, including the Generalized Cowling Nomenclature and the classification based on Modal Properties, are explored in this work. These schemes provide complementary information about the modes, enabling proper classification. They are applied to study non-radial oscillations of protoneutron stars and to infer properties of the pulsating protoneutron star from gravitational wave signals. Linear perturbation theory is applied to the protoneutron star, using a Lagrangian description of the fluid perturbation. Hydrostatic protoneutron star configurations are obtained from 3D core collapse supernova simulations. The Tolman-Oppenheimer-Volkoff equations are solved to reconstruct the structure of the protoneutron star and the spacetime geometry. The line element describing a static spherically symmetric conformally flat spacetime is used, and the Lagrangian displacement vector is employed to describe fluid perturbations. The functions eta r and eta depend only on the radial coordinate r, with a time dependence I sigma t assumed for each perturbing function. Classifying protoneutron star modes requires solving a set of four coupled differential equations for variables eta r, eta, f alpha, and delta alpha, which describe perturbations in the star's interior, including the radial component of gravitational acceleration, g. Derived from linearized Einstein field equations and hydrodynamic equations, these equations are solved subject to boundary conditions at the stellar radius, r, and the center of the protoneutron star. The boundary condition at the stellar radius is delta p equals 0, where delta p is the Lagrangian perturbation of pressure, satisfied when the stellar radius is defined as the point where mass density ρ equals 10 to the power of 10 gcm cubed. At the center, solutions must be regular, implying eta r, f alpha, and delta alpha vanish at r equals 0. The equations are solved using a shooting method with Ritter's root-finding algorithm, searching for eigenfrequencies between 100 Hz and 2000 Hz. A Runge-Kutta-Felberg integrator is employed to solve the equations at every time step of the protoneutron star evolution. This work utilizes 3D simulation models of core collapse supernovae from Radice et al. 2019, which employ the f/o.pc/r.pc/n.pc/a.pc PC code to solve equations of neutrino radiation hydrodynamics. The simulations account for gravitational redshift, Doppler effects, and inelastic scattering, and employ the relativistic Cowling approximation to simplify the equations by neglecting metric perturbations. This approximation reduces the equations to 2, 13, and 14, describing fluid perturbations and used to find mode frequency, sigma, and associated eigenfunctions, eta r and eta. The models used have ZAMS masses ranging from 9m to 60m, with details listed in Table 1. Simulations were performed using the SF-Ho equation of state of Steiner et al. 2013. The classification methods are strictly valid only when metric perturbations are neglected, and the relativistic Cowling approximation is employed to simplify the equations, resulting in 13 and 14, used to find sigma and associated eigenfunctions, eta r and eta. Classification of modes in a neutron star, NS, is a complex task, particularly in the dynamic environment of a protoneutron star, PNS. The Cowling classification scheme, based on the number of nodes in the eigenfunction, is commonly used, but its applicability is limited in a PNS due to the dynamic nature of the star. In this context, the Generalized Cowling Nomenclature, GCN, provides a more suitable classification, as it is based on the difference between the number of p-nodes and nodes, which increases monotonically with mode frequency and remains conserved as the star evolves. The GCN classification is illustrated in the phase diagram in Figure 2, where the number of p-nodes and nodes are identified by the direction of the curve. However, this scheme does not provide insights into the character of the mode. To address this limitation, the character-based mode property, CBMP, scheme was introduced by Shibahashi and Osaki, 2000. This complementary classification considers the modal property, offering a deeper understanding of the mode's character. The radial eigenfunction profiles for various modes, shown in the top panel of Figure 2, demonstrate the differences between P1 mode, fundamental mode, and G1 mode. The CBMP classification, presented in the bottom panel of Figure 2, categorizes modes based on their properties, providing a more nuanced understanding of the mode's characteristics. The employment of both the Cowling and GCN schemes, in conjunction with the CBMP scheme, provides a comprehensive analysis of mode classification in a PNS. These classifications are essential for understanding the characteristics and evolution of modes within the dynamically evolving environment of a PNS. The GCN and CBMP schemes offer a more complete picture of the modes, as they account for the loss or gain of nodes during stellar evolution and provide insights into the mode's character, respectively. The authors present three approaches for classifying PNS oscillation modes, demonstrated through a representative example in Figure 2. The Cowling classification, GCN, and CBMP methods are used to identify modes, which are represented by the same colors but classified differently according to each method. The CBMP classification is based on the characteristics of the main trapping zone of the oscillation mode, categorizing modes into two types by identifying their main trapping zones. The authors define terminology for this classification, including G_n, P_n, and G_n, which indicate modes trapped mainly in the core zone, p propagation zone, and g propagation zone, respectively, with n nodes. A key quantity for this classification scheme is the ratio of the kinetic energy of the oscillation mode within the core to that of the whole star, denoted by delta, equation 17. If delta is close to zero, the mode is trapped in the envelope, otherwise, it is trapped in the core. The threshold, delta_critical, is an arbitrary parameter used to determine whether a mode is trapped in the core or envelope. The authors apply this classification to 10 models of PNS evolution, considering only quadrupolar, L equals 2, modes, which are expected to be the most energetic in gravitational wave radiation from PNSs. The frequencies of the modes are calculated in the Cowling approximation at every 10 milliseconds in each model, and the modes are classified using the 3 different classification methods described. The results of the classification highlight the advantages of the CBMP classification, which provides information about the region of the star that contributes the most to the GW emission. In the post-bounce phase of a supernova explosion, neutron star modes undergo significant evolution. This paper presents a comparative analysis of 3 different mode classification methods: the Cowling approximation, the Generalized Cowling Approximation, GCN, and the Core Envelope Mode Pairing, CBMP, approach. The authors analyze the time evolution of mode frequencies for various PNS models, showcasing similarities across all models. The GCN and CBMP classifications provide a more detailed understanding of the mode evolution, particularly around close approaches, or avoided crossings where the Cowling approximation is less accurate. The GCN reveals that these close approaches appear as avoided crossings, simplifying the mode evolution description. In contrast, the CBMP identifies an additional mode, G0, and differentiates between modes trapped in the core and envelope based on their node numbers. The paper also explores the emission of gravitational waves by the PNS, comparing the time-evolving spectrum of modes with the spectrogram of the GWs for Model 9. This analysis utilizes the GCN and CBMP classifications, highlighting the evolution of the F mode and its connection to GW emission. Overall, the paper demonstrates that the GCN and CBMP provide more comprehensive descriptions of neutron star mode evolution than the Cowling approximation, especially in the context of supernovae physics and gravitational wave emission. The classification of pulsar neutron star (PNS) modes is approached through 3 distinct methods. Figure 4 illustrates the time evolution of mode frequencies classified using the Generalized Cowling Number (GCN) for PNS Model 1. The middle panel displays the time evolution of the ratio between the kinetic energy of oscillations within the core and their total kinetic energy inside the star for the P1, F, and G1 modes. The horizontal line indicates the threshold in delta used for the Cowling-based mode parameterization, CBMP, while the shaded region represents possible thresholds of delta that give qualitatively the same result. The bottom panel shows the time evolution of the mode frequencies for the same model, now classified using the CBMP. Notably, the GCN-F mode exhibits excellent agreement with the strongest gravitational wave emission and minimal avoided crossings. This suggests that the PNS spectrum evolves with avoided crossings, resulting in gravitational wave emission mainly through an F mode that rapidly alternates between being trapped in the core and envelope of the PNS. The CBMP classification provides valuable information, including the characterization of the modal properties of the GCN-F mode and the identification of avoided crossings. Table 2 presents the best fit parameters for quasi-universal relations of the form f, x, equals a plus bx plus cx squared, describing the CBMP mode frequency f in Hz as a function of x equals square root m r cubed in units of m caret 1 km caret 3 s caret 2. These relations facilitate the inference of neutron star properties using gravitational wave detection. The study examines quasi-universal relations between mode frequencies and macroscopic parameters, such as mass and radius, for cold neutron stars. The results indicate that the frequency of the fundamental mode of cold neutron stars scales with square root m r cubed, with minor dependence on the equation of state. The classification of modes with the CBMP yields simple, monotonic behavior, independent of the progenitor mass. The fits to this novel quasi-universal relation are presented in Table 4.3. The asteroseismology of PNSs is complex due to their dynamic and temperature-dependent nature, and this study explores three methods for classifying their non-radial modes of oscillation. In the context of post-supernova neutron star (PNS) oscillations, researchers have employed various mode classification methods to study the fundamental F mode and its role in gravitational wave (GW) emission. Three distinct approaches are examined: Cowling, GCN, and CBMP. The Cowling method, which relies on identifying a nodeless F mode, is underdetermined at early times due to the absence of this mode. In contrast, the GCN method, based on identifying p-end nodes, allows for tracking mode evolution and reveals marked avoided crossings at early times, where two modes exchange character. Notably, the gene-identified F mode exhibits good agreement with simulated GW emission, suggesting that the region responsible for most GWs alternates between the core and envelope at early times. The CBMP, applied for the first time to study PNS oscillation modes, follows the time evolution of sequences of modes with the same properties, revealing a simple and monotonic behavior with no avoided crossings. This approach provides fits for quasi-universal relations describing the most relevant mode frequencies as functions of the PNS average density. A matching classification scheme by Torres-Forney et al. 2019b produces similar results to the CBMP, while the ramp-up mode discussed by Mori et al. 2023 is similar to the F mode described by the CBMP. The primary advantage of the CBMP lies in its ability to provide physical information on the part of the PNS where GWs are most likely being produced. Future research directions include extending the GCN and CBMP to provide more detailed insights into the physics of PNS oscillations and GW emission. The authors present three approaches for classifying pulsar neutron star (PNS) modes, focusing on the graph convolutional network (GCN) and covariant basis mode projection (CBMP) methods. They compare the performance of these methods in identifying mode sequences in the spectrogram of gravitational wave (GW) emission from a simulated model. The GCN shows better agreement with the simulated GWs at earlier times, while both methods agree on the F mode classification at later times. Figure 6 displays the spectrogram of the GW emission, highlighting the GCN and CBMP mode sequences. Notably, the GCN sequences exhibit avoided crossings, which are absent in the CBMP sequences. The CBMP sequences, however, show simpler trends, making them easier to analyze. Figure 7 presents the relation between macroscopic quantities, mass and radius, and the frequencies of modes classified using the GCN and CBMP. The top panel shows the GCN sequences, while the bottom panel displays the CBMP sequences, with the black lines representing the fits to each mode in the CBMP and the shaded areas representing the 1 sigma bands of each fit. The frequencies corresponding to the G0 modes below the F modes in the bottom panel are not included in the top panel, as they are classified as G1 modes in the GCN. The authors acknowledge the limitations of their work, including the need to extend the CBMP criteria beyond the Cowling approximation. Da does not equal 0, and to calculate the modes using time-dependent perturbation theory. They suggest checking the quasi-universal behavior of the mode frequencies against simulations with different progenitor masses and additional equations of state. Furthermore, they emphasize the importance of assessing the detectability and reliable identification of these modes in a galactic core collapse supernova, which could provide insights into the properties of such events up to the Large Magellanic Cloud. Gravitational waves from neutron star oscillations offer a unique window into the physics of these extreme objects. Understanding neutron star physics is crucial for advancing our knowledge of astrophysics and cosmology. Theoretical frameworks for stellar oscillations, including the Cowling approximation, adiabatic approximation, and treatment of non-adiabatic effects, provide the foundation for studying neutron star oscillations. Three primary types of neutron star oscillations are radial, non-radial, and R modes, each with distinct damping mechanisms. The Chandrasekhar-Friedman-Schutz (CFS) instability plays a significant role in R modes, potentially leading to the emission of gravitational waves. Magnetic fields also impact neutron star oscillations, influencing the frequency spectrum and stability of these oscillations. Rotation alters the frequency spectrum and stability of neutron star oscillations, while superfluidity and superconductivity affect the damping of these oscillations. The detection of gravitational waves from neutron star oscillations is a promising area of research. However, further study is necessary to fully understand the potential for such detections. Theoretical models and simulations are required to better comprehend the complex physics underlying neutron star oscillations and their associated gravitational wave emission. Advances in this field will have significant implications for our understanding of neutron star physics and the role of gravitational waves in astrophysics and cosmology. Key research areas include refining theoretical models of neutron star oscillations, understanding the impact of magnetic fields and rotation on oscillation modes, and exploring the role of superfluidity and superconductivity in damping oscillations. By addressing these challenges, researchers can unlock the potential for detecting gravitational waves from neutron star oscillations, providing new insights into the behavior of these extreme objects. The impact of varying delta critic values on the classification of post-bounce oscillations in a protoneutron star, PNS, is examined using the core bounce model with perturbation, CBMP. This model classifies modes based on their trapping regions within the star. The time evolution of mode frequencies is analyzed for delta critic values ranging from 0.2 to 0.5. The results indicate that modes change character at different times depending on the delta critic value. Specifically, for larger delta critic values, modes initially trapped in the core or envelope become trapped in the envelope or core earlier or later, respectively, compared to smaller delta critic values. The qualitative outcomes remain consistent across the range of 0.2 is less than or equal to delta critic is less than or equal to 0.5, despite the changes in mode trapping regions. Figure A1 illustrates these findings, displaying the time evolution of mode frequencies for various delta critic values. Each panel demonstrates how the mode's trapping regions shift as delta critic changes, affecting the timing of their character changes. This analysis highlights the sensitivity of mode classification to the choice of delta critic and underscores the importance of accurately determining this parameter in PNS oscillation studies. The CBMP model's classification of modes is based on the trapping regions within the star, which are sensitive to the choice of delta critic. The results show that the timing of mode character changes is affected by the value of delta critic, emphasizing the need for precise determination of this parameter. The consistency of qualitative outcomes across the examined range of delta critic values suggests that the CBMP model is robust, but the sensitivity to delta critic values highlights the importance of careful parameter selection in PNS oscillation studies.